I'm going to start with a quick recap of the background that I gave in the first lecture. So, as I've told you, the sort of key idea in all this is that quantum theory is a special case of a much wider physics, that we're stuck in a certain region where the probability distributions of certain hidden parameters are given by the Born rule, but in principle there's a much wider physics out here, and that the reason we're in here is because of some sort of relaxation process that took place sometime in the past. I've looked at a particular hidden variables theory due to de Broglie and further developed by Bohm, in which a system has a configuration. It might be a many-body system of particles. It has a certain configuration whose velocity is determined by the gradient of the phase of the wave function. And the wave function is regarded as a sort of guiding wave that exists in configuration space. And you get equivalence to quantum mechanics if the initial distribution of these configurations is psi squared. Something Carlo asked me in the first lecture is this business about, well, what do you mean by hidden variables? I'm not sure I explained it terribly well. I think maybe a better way would be to put it this way, that we are able, in the lab, we are able to control the wave function in the sense that I can easily prepare a particle with a given initial wave function. I put it in a box, I do certain operations, I know the wave function is such and such. What we cannot do is prepare the following. The particle is in the box, its wave function is such and such spread over the box, and the particle is here. We don't know how to do that. We cannot prepare and control the initial positions. And ultimately, in this theory, the reason is that the systems you extracted the particle from already had this kind of statistical ignorance in them. Okay, they'd already reached this equilibrium distribution. And if you think this through, if I go in the lab and I pick out an electron from some collection, if this parent ensemble already has a psi squared distribution, when I put the electron in a box and prepare its wave function, it's going to have this psi squared distribution with that wave function. You can show these things. So there's a kind of, we're not able to control the initial conditions for these positions when we're in equilibrium, and that's why, in a sense, I think it's fair to call them sort of hidden variables. Anyway, just a detail. Let me now say, and of course illustrating for one particle, as I told you, this pilot wave obeys a Schrödinger equation, which implies the usual continuity equation. If we assume that all particles obey this guidance equation, then a distribution of these particles will necessarily evolve in accordance with this continuity equation. Now, I could begin with any initial distribution P and evolve it forward in time according to this equation. If P happens to equal psi squared initially, then it remains psi squared for all T, because I have the same two differential equations here. And this argument generalizes really pretty any system with a configuration and a wave function in configuration space. But if instead P is not initially psi squared, then what happens? So here's an example I showed you. This is a particle in a box prepared with a wave function that's a superposition of the first 16 energy states. Psi squared evolves according to the Schrödinger equation. The actual density P evolves according to this continuity equation. If you evolve forward in time, you find it relaxes very closely to the quantum distribution. So this is the relaxation to quantum equilibrium. All the systems that we see, have experimented with, have this equilibrium distribution. If this relaxation process did occur, when did it occur? It's easy to estimate. You might be wondering about timescales. If you look at this example here, this wave function here is periodic. And the time scale from here to here is essentially the time scale over which the wave function evolves, okay? And you see that the relaxation time scale is comparable. So you imagine if I have an electron in an atom that was a superposition of 16 energy states, the relaxation time scale is going to be the sort of atomic time scales, okay? So clearly, if I want to if there was non-equilibrium in this system now, and this is in some superposition, it's going to very quickly just disappear. The difference between these distributions can be quantified by this h function. It quantifies the sorry, here's rho before I was using p. It's what happens when you recycle slides from different talks. Apologies. But this is the density, here is psi squared. This is minus the relative entropy of rho with respect to psi squared. It measures the difference. It obeys a coarse-graining h theorem. And in this numerical simulation, here's log h against t. This is the coarse-grained h. It decays exponentially. There's an exponential decay of this h function. So this relaxation is a pretty efficient, robust process. And this exponential decay has been verified by other simulations in a variety of conditions for these kinds of systems. Now, when might this have occurred? So presumably it occurred a long time ago. Any system that we have access to, this hydrogen atom in the lab, as I said the other day, it has a history. It has interacted with things. It hasn't just been sitting in a vacuum for billions of years. If this process occurred, it will have occurred way back in time. And so there's a hypothesis here that we could regard quantum noise as a relic of the Big Bang. So let's go back to the Big Bang and see if we can figure out when and how fast this might have happened, and so on and so forth. Okay, so maybe quantum theory, seeing as now inflationary cosmology tells us these hot and cold spots in the CMB are in effect a photograph of quantum fluctuations at very early times, we have a hope of testing the Born rule in the very early universe. Okay, that is the recap of basically what I said a couple of days ago, and that only took me 7 minutes, so that's not bad. Okay, so now it's a very mixed audience, so I'm going to give you a 3-minute cosmology crash course. Okay? There are a lot of interesting philosophical questions, I think, in this area, the CMB, how people analyze the statistics, what this theory, how this theory works. And the essentials actually involve very little. You might think it involves a lot of complicated general relativity, field theory. So actually, the essentials can be understood with remarkably little. For a start, the universe is, to a first approximation, a very good approximation, is flat. Flat and expanding. And this is right back to early times. Now, if you forget about that factor A, this is just the line element of special relativity, proper time relating to coordinate time and the displacement in space. What is standard what this factor A is a function of time that's increasing. It tells you the universe is expanding. And it's conventional to take this A to be 1 today. So what you can think of is that today A is 1, and these coordinates x are just your usual physical coordinates today. And t is a time defined by just the average cosmic rest frame. Or there is an average cosmic rest frame. Earlier in time, when A is less than 1, a coordinate distance dx corresponds to a physical distance, A of t. So physical distance is smaller in the past. A physical wavelength, let's say I'm talking about some field on space. It might be perturbations in some scalar field or in some density. If I look at it in Fourier space, I'll be talking about modes with different wavelengths. The physical wavelengths also grow with time. And the physical wavelength is just defined to be this. Lambda here is again the proper wavelength today when the scale factor is 1. So please bear this in mind. Physical wavelengths are growing, they're proportional to the scale factor. If I had, for example, a universe where the equation of state is dominated by radiation, you know from the Einstein equations, the scale factor will grow as the square root of t. That's, okay, Cosmology Crash Course, Part 1. Cosmology Crash Course, Part 2, the Hubble Radius, important parameter. The Hubble parameter is just defined to be, this is the time derivative of the scale factor, A dot. So it just measures the rate of spatial expansion. And it varies with time. It used to be called the Hubble constant, but it varies with time. It's a parameter. The Hubble radius is just the inverse of that. So for example, if I have a scale factor going as t to the half, the Hubble radius you can work out is equal to a divided by a dot is equal to 2t. This is a characteristic length scale. It depends on, at a given time, you have a certain characteristic length scale. It can also be regarded as a time. We're taking speed of light is 1, so the Hubble time or the Hubble radius. There's a lot of confusion in the literature. This is often referred to as the horizon. It's not a causal horizon. It's not like, event horizon, light cones, and so on. It is more like, in a sense, maybe a dynamical horizon, in the sense that perturbations, the propagation of perturbations tends to be damped on length scales larger than this length scale. So, but anyway, there are two important regimes here. This characteristic length scale sets a dividing line between two important regimes. The short wavelength limit, or the sub-Hubble limit, where the physical wavelength is much less than the Hubble radius. There you should recover local Minkowski physics. The physics should not feel the effect of the expansion and so on, like in this room. We do calculations, quantum field theory, you don't have to worry about the fact that the universe is expanding. The long wavelength limit, where the physical wavelength is bigger than the Hubble radius, if you have some classical perturbations with such large wavelengths, they tend to freeze and not evolve. It's a characteristic of perturbation theory on expanding space. Okay, so now we can talk about sort of standard, quote, standard picture of modern cosmology, that we see the cosmic microwave background with some small temperature anisotropy. These photons decoupled at a time about 400,000 years after the Big Bang, when matter was almost homogeneous. The small inhomogeneities, for instance, in the local gravitational potential, generate small differences in energy frequency of these photons. These perturbations at this time grew from perturbations at an earlier time. Now there's a crucial thing here, that during this radiation-dominated period, A proportional to the square root of t, physical wavelengths, as you will recall from your cosmology crash course, go as proportional to the scale factor, proportional to t to the half. Whereas the Hubble radius is equal to 2t, or it's just proportional to t. What does this mean? It means that the physical wavelengths are growing. Hubble radius is growing. But the Hubble radius is growing faster than physical wavelengths. So if I have a physical wavelength that at this time is larger than the Hubble radius, it's outside the Hubble radius, as often said. As time goes on, this physical wavelength will enter the Hubble radius. The physical wavelength will become less than the Hubble radius. Now what happens when a physical wavelength is larger than the Hubble radius? It tends to be frozen. The perturbation doesn't evolve. As the physical wavelength gets smaller than the Hubble radius, it starts to evolve and grow to generate the perturbations that existed at this time when photons decoupled. Okay? Now, where did these perturbations at this super Hubble length scale come from? This was thought to be a mystery up until about 1980. It is now thought, according to inflation, there was an earlier period of exponential expansion. So the scale factor here is expanding exponentially. The h here is a constant, and that h is just the Hubble radius. If you look at a over a dot for this, it's just the same constant. What happens here? The Hubble radius is constant. Physical wavelengths are growing exponentially. During this period, I have quantum fluctuations in the vacuum state, whose wavelengths grow exponentially and exit, quote, exit the Hubble radius. They grow larger than the Hubble radius, and they end up sitting out here, waiting later on to enter the Hubble radius and seed the formation of these perturbations and the anisotropy in the CMB. Okay, this is sort of standard picture now. Okay, so what is happening? There's a mapping from, we look at the sky, we deduce what these perturbations look like when the photons last scattered. We deduce from our cosmological perturbation theory what the primordial spectrum of curvature perturbations look like out here. these perturbations were generated according to inflation by quantum fluctuations in here. Okay? So now the logic should be pretty clear that the statistics of the cosmic microwave background ultimately traces back to the statistics of these quantum fluctuations. If I change the Born probability rule here, I'll change the spectrum of the inflaton fluctuations, change the spectrum of the curvature perturbations, change the spectrum of all of this. So this is how inflationary cosmology can be used as a laboratory to test quantum mechanics at very early times. So now let me put a bit of math. So that's the physical picture, which is enough to follow this talk. Those who want to see a bit of mathematical detail, so there are standard formulas for how an inflaton, so there's some scalar field during inflation, which has a sort of homogeneous part that's classical and is driving this exponential expansion. And there is a perturbation that is quantized. And the fluctuations of the quantum fluctuations of this generate the curvature perturbation according with this formula. Basically, the curvature perturbation in Fourier space is proportional to the field perturbation. This phi 0 is the homogeneous part of phi that's slowly varying during inflation. This is the Hubble parameter during inflation that is almost constant but not quite. And this is evaluated at a time when the physical wavelength has grown much bigger than the Hubble radius during inflation. This is how an inflaton perturbation generates a curvature perturbation. There is then a standard formula for how a curvature perturbation generates anisotropy in the CMB. This function here, the transfer function, encodes the complicated astrophysics, okay, of how these perturbations affect the CMB. And the temperature anisotropy, this small ripple that we see on the sky as a function of angle on the sky, can be expanded in spherical harmonics. These coefficients are given by this formula. Okay, so you see how we're going from primordial perturbation, curvature perturbation, to the temperature anisotropy. And as I mentioned briefly, let me say this again, I think this is an interesting point, is that in principle, well, there's one sky, there's one perturbation, there's one set of coefficients here. In order to do statistics, the following assumption is made, which I think it would be nice if some philosophers, people interested who really know about philosophy of probability and statistical inference would look at this, what is really going on. It is assumed that the temperature function we see on the sky is one realization of some sort of stochastic process. There is an underlying probability distribution for the temperature function, which you could, however you want to think about that, it's up to you. There's some theoretical ensemble of skies, if you like. If you assume that that probability distribution is rotationally invariant, you can show that the marginal distribution for these coefficients is independent of m. For a given value of L, the marginal probability does not depend on m. So for a given L, say L is 100, I have 2L plus 1, I have 201 coefficients that I've measured that all came from the same probability distribution. So for large L, I can actually probe that theoretical probability distribution. Now if it sounds weird, well that is the way this analysis is done. And of course if L is small, if L is 3, I only have 7 coefficients. I've measured 7 realizations of one probability distribution. My statistical best estimates, best fit, so on, are going to be subject to what's called cosmic variance. Okay, so you can accurately probe the probability distribution for larger L. Anyway, I think it's a good topic to think about. What does this mean really from a sort of philosophical point of view? But anyway, so this theoretical, these coefficients that we measure, one can think about what is the mean of the square of these coefficients for the theoretical ensemble. This is called the angular power spectrum. And the measurements of the CMB, these plots that you see, are a best fit to the data of what the theoretical angular power spectrum is supposed to be. And it's usual to plot L plus 1 multiplied by CL, because then this function, it tends to flatten out here. Anyway, from the preceding formulas, you can show, if you assume that the probability distribution for the curvature perturbation is translationally invariant, so there's some kind of statistical homogeneity, you can write the angular power spectrum in this form. It's the square of the transfer function times this power spectrum for the curvature perturbation, which is just defined to be k cubed. K is the wave number times the mean square. This V is a normalization volume taken to be very large. Remember, the curvature perturbation is essentially proportional to the inflaton perturbation. So this mean square is going to be proportional to the mean square of the inflaton fluctuations. Okay, so the mean square of the inflaton fluctuations feeds into this, which feeds into that, which feeds into the thing that you're plotting here. Okay, so it's all.
Antony,
yes.
The first formula, what happened to M?
Good, thank you. So, as I said, if you assume statistical rotational invariance, the probability distribution for these coefficients is independent of M. It depends only on L. So the expectation value for this will depend only on L. Okay, so there's no M on the left-hand side.
And that is why the error bars are larger.
Yes, now you see what is often plotted, I don't really see here, often you will see in these plots, you'll see a band that grows here. And that is that they're showing you the size of the cosmic variance. So they're showing you that there's an inherent uncertainty here. And you know, what it is, this, when you look at the when you measure these 2L, for a given L, you measure these 2L plus 1 coefficients. If you just take the arithmetic mean, you get a quantity whose expectation value will equal this expectation value, the theoretical expectation value. So in other words, if I average these measured quantities, that thing is an unbiased estimator for the theoretical thing that we're trying to get a grip on. But there is some variance in the value. Okay. Anyway, so here we are, primordial power spectrum for curvature perturbations, where these are generated by the inflaton perturbations. Okay, what about the inflaton perturbations during inflation? These are calculated using quantum field theory, assuming the natural vacuum state of this exponentially expanding space. In quantum, from a de Broglie point of view, what you calculate in quantum field, what you calculate in quantum field theory is the quantum equilibrium value. This variance comes out to equal this is just a normalization volume. This is the Hubble parameter during inflation. Here is the wave number. The power spectrum that's defined to be k cubed times this is just this quantity that does not depend on wave number. That's why it's called scale invariant, is independent of wavelength. The power spectrum for the curvature perturbation, which curvature perturbation is proportional to phi, just comes out to be this. If I assume this quantum equilibrium value, the quantum theoretical prediction for the curvature perturbation comes out to be this here, where this is, as I said, evaluated at a time where the physical wavelength has grown well outside the Hubble radius. During inflation, this homogeneous part of the inflaton field is, so there's this slow roll, it's varying slowly, and the Hubble parameter is varying slowly. So these things are almost but not quite constant. So you predict a spectrum that's almost scale invariant, small tilt, okay? Those are the quantum theoretical predictions, and they match observation pretty well. What if I have quantum non-equilibrium during inflation? What happens? Let me tell you that, so in this paper in 2010, I discussed let me just tell you about what the quantum vacuum state looks like during inflation. It is a product state over these. So these are the, sorry, I don't know if I think on another slide I've defined these things. We're taking these are the Fourier components of the inflaton field, and I take the real and imaginary parts as my degrees of freedom, okay, for a given mode. And of course, there are a whole infinite number of modes. The Bunch-Davies vacuum, which is the natural vacuum during inflation, is a product over these modes. And the wave function, this is the quantum wave function in that vacuum, is time dependent. It's a Gaussian that is contracting in time. It contracts in time until it just reaches a certain point and stops. That is the quantum psi-squared distribution. Now, this wave function, you can calculate it, and you can calculate the de Broglie-Bohm trajectories. This is what they look like. Here, eta is what's called conformal time. So it runs from minus infinity. If I've got this infinite exponential expansion, it will run from minus infinity to 0. You see these trajectories, they're just starting out, they're just coming in, and then they're just stopping. So if I have some arbitrary non-equilibrium distribution, it just gets contracted in exactly the same way that the wave function gets contracted. There is no relaxation. During inflation, if there was non-equilibrium at the beginning of inflation, it will not relax because the de Broglie-Bohm velocity field is just too simple. The time evolution, to get relaxation, you need some complexity, some complicated evolution of the trajectories, like as we saw in the box. Here it's very simple. The non-equilibrium distribution just gets squeezed in the same way as the wave function gets squeezed. What that means is that the variance, the width of this, the ratio of the width of the quantum distribution to the non-equilibrium distribution is constant in time. Okay, the ratio of these widths doesn't vary with time. And it's the width, the variance, that comes into the power spectrum. So basically, if at the beginning of inflation, the actual width of the inflaton distribution is equal to the quantum width multiplied by some factor, at later times it'll be the same. Okay, it'll still be just that same factor that is not dependent on time. So this means that any initial non-equilibrium at the beginning of inflation is just basically frozen in there. It's just the wavelengths are changing, but that's all. So the power spectrum, if I had non-equilibrium during inflation, the power spectrum is just going to be modified by some arbitrary function. It would, whatever the ratios of the widths were at the beginning. So basically now we have an arbitrary function, the arbitrary non-equilibrium distribution at the beginning of inflation. You can set empirical limits on this. If you look, we know that the power spectrum matches pretty well with the quantum prediction. So for example, this S here is what I call the hidden variable entropy. It's just the negative of that H function I defined. It's equal to 0 when you're in equilibrium. You can put an upper bound, just looking at data. There's a simple rough bound to give you an idea. Clearly, quantum equilibrium, if all this sort of theory is true, is pretty accurately correct during inflation, at least on this sort of length scale here, which is okay. But now, okay, putting empirical bounds on this non-equilibrium function, if you like, is one thing. What about trying to predict something about this function? Okay, I mean, one can do phenomenology, just looking at data, what's the best fit, what are bounds on the non-equilibrium that existed during inflation. But could I make some prediction? So here's an idea, let's imagine, and there are theories in which this is true, that before inflation, there was some pre-inflationary era, which could have been, to be definite and for simplicity, let's assume there's some radiation-dominated era here. So it's sort of with a scale factor going as t to the half. And at the end of this radiation-dominated era, something happened and inflation started to occur. Now, what we can do is during inflation, there's no relaxation. But during a radiation-dominated era, we expect relaxation to occur, at least for short wavelength modes. And as I'm going to show you, relaxation can be suppressed for large wavelength modes. So the idea is that by looking at relaxation in this pre-inflationary period, we could make some kind of prediction, or at least a good guess, as to where non-equilibrium, for which modes could non-equilibrium still exist as I enter the inflationary period. And once they're there at the beginning of inflation, as I've said, there's no relaxation during inflation. They'll just stay there and then feed into all this that we see in the CMB. So now, here I'm going to present that there is, in fact, in a radiation-dominated expansion, in de Broglie-Bohm theory, there is a natural mechanism for the suppression of relaxation at long wavelengths. There are some earlier papers where I argued for this. Recently with Samuel Collin, who's a postdoc with me at Clemson, we've looked at an exactly solvable model of this and done some nice simulations that I'm going to show you. And this work here is actually funded by the Templeton Foundation, I should say. Anyway. And it so happens, recent evidence from the Planck satellite is there is evidence for a power deficit at long wavelengths in the CMB. So I'm now going to try to show you how these things could be connected. Okay, now what I'm going to do now, there's going to be some mathematics and stuff which you don't really need to follow, because I'm just going to tell you in simple physical terms what it means. But I know that if I go now through 6 or 7 slides of that, various people are going to fall asleep and you're going to miss the punchline. So I'm going to give you the punchline now while people are still awake. Okay, the punchline is this. So if you will just first look at the left-hand side, we're looking at one mode. What we're doing, we have a pre-inflationary period, and we're just looking at some scalar field. What it corresponds to doesn't matter, and it's just a simple field. It might be related to the inflaton field later, it might not, but it's just some scalar field in this pre-inflationary era. And in Fourier space, we're looking at one mode, okay, one mode with a certain wavelength. And what we do is we're interested in what happens at long wavelengths. So this mode we take it begins with a physical wavelength that is larger than the Hubble radius. Now remember, during a radiation-dominated expansion, the physical wavelength ends up becoming less than the Hubble radius. It enters. What we do is we calculate the time evolution from this time, the physical wavelength is super Hubble, we calculate to the time where the mode enters the Hubble radius, okay? Now what we do, we have, so there are these, let me just remind you, there are these, for each component of the inflaton field in Fourier space, there are these 2 real degrees of freedom. So for one mode, I've got this 2-dimensional parameter space, okay? And what I'm doing here, this is the initial density for the psi squared, the quantum Born rule. What I have is an initial I've got the initial wavelength at super Hubble for this mode. The mode begins with a wave function that is a superposition of the first 25 energy states. The ground state plus and these energy states, this mode mathematically is like a harmonic oscillator. The Hamiltonian is like a harmonic oscillator, but with a time-dependent mass and frequency. So, but anyway, I've got the first 25 energy states in a superposition with random phases. This is what the psi-squared distribution looks like. And this is how it evolves in time as the wavelength becomes less than the Hubble, eventually is equal to the Hubble radius. This is at the time t enter. The actual support of psi squared actually shrinks in configuration space. So we do a rescaling. That's why there are these primes here. We do a rescaling to factor out this shrinking. Okay, really this will be getting smaller and smaller. Okay, so these are rescaled distributions. This is the time evolution of the Born quantum probability. Now, we take an initial non-equilibrium distribution that is just some simple Gaussian that is in fact equal to the quantum ground state probability. Okay? This is what the initial non-equilibrium distribution looks like. And we evolve forward in time. And you see it starts to evolve. This is with expanding space. Okay? This is this field system on expanding space. what happens? If you look at this, this distribution is spread out, but if you only evolve up to this time, it has not spread out to the full width of the quantum distribution. This is narrower than the quantum distribution. Okay, it is approaching equilibrium, but it's only sort of got halfway there or something. Okay. Whereas if I do the same calculation, but I just set the scale factor equal to 1, a constant, there's no spatial expansion, and you do the same calculation over the same physical time period, this is what you get. This is your psi squared evolving. I've got 25 modes in superposition. This initial non-equilibrium evolves, and it, at the end of the same time period, it matches almost exactly in extent, in width, and in fine details the quantum distribution. So this is the very efficient relaxation, similar to what I showed you in the box, when space is not expanding. When space is, and I should say, if this physical wavelength, instead of initially being super Hubble, it had been sub-Hubble, very short wavelength, you know you recover the same equations as when there's no expansion. Okay? So what is this telling you? It's telling you that if I start with identical initial conditions, same wave function, same initial non-equilibrium distribution, for very short wavelength modes, it's just going to relax to equilibrium over a certain time. Bang, you've reached equilibrium. The long wavelength modes over the same time period will not reach equilibrium. There is some kind of retardation or suppression going on expanding space. Now, how did we show that? Let me sort of go through the pilot wave field theory on expanding space. It's straightforward. The flat metric, a minimally coupled massless scalar field. The Hamiltonian is just a collection of harmonic oscillators with time-dependent mass and frequency. One can write down a Schrödinger equation for that, a continuity equation. The de Broglie velocities for these field variables are just, again, the gradient of the phase, but there's a 1 over a cubed. A is changing with time. Initial distribution follows this continuity equation, and so on. But we're looking at one decoupled mode. The total wave function is the wave function for the mode times the rest of the something that depends on the rest of the variables. If we drop this index and I define a quantity m that's a cubed, so this is a sort of effective mass that is proportional, that is equal to the cube of the scale factor, and this time-dependent angular frequency. The dynamical, don't worry about these equations, I'm going to tell you in words what they mean on the next slide, and it's very simple. That for the decoupled mode, this is the Schrödinger equation, the guidance equation, the equation for the evolution of an arbitrary density. What does it mean? What it means, these equations, never mind about these equations, for a decoupled mode that's not entangled with the rest of the field, these are identical to the equations for a non-relativistic particle moving in a two-dimensional harmonic oscillator potential, except the mass is time-dependent. It's equal to the cube of the scale factor. The angular frequency is time-dependent. It's going as k over a. So if you imagine, if I have a two-dimensional box or something, a harmonic oscillator potential, I have a non-relativistic particle moving in it, and with this time-dependent mass and angular frequency, and I do the sort of simple elementary quantum theory of that and the de Broglie theory of that, mathematically it is exactly the same as this system. Now, this system of equations, this oscillator with this time-dependent mass, has the following interesting property, that its time evolution in quantum theory and in de Broglie theory, well, we found an exact solution for the time evolution of the wave function when the scale factor is going as a square root of t. And we're able to show, never mind these equations, the point here is this, the de Broglie evolution from some initial time to a final time is identical to that of a standard harmonic oscillator from the initial time to a retarded time, which is given by a certain formula. This function appears in the solution for the wave function, never mind what it is, and there's some rescaling of coordinates, never mind. But the point is the following, that what I can do is I want to evolve my field system on expanding space from some initial time to a final time. What I can do, I can take an ordinary oscillator with a constant mass and frequency, with the same initial wave function. If I evolve from an initial time up to a retarded time, then the final positions distribution will be exactly the same. There's a mapping between them. Okay? So what this means is, here's a plot of the retarded time versus ordinary time. And you can see it's smaller than t. So this is the point, this thing, now all this stuff, in words, the time evolution of the real system on expanding space over this time interval may be obtained by evolving the equivalent standard oscillator with the same initial conditions over the shorter time interval up to this retarded time, where this is a known function that we've calculated. Now this retarded time has some interesting properties that if you look at it, well, as you might expect, in the short wavelength limit, it reduces to physical time. There's none of this retardation. In the far super Hubble limit, where the wavelength is much bigger than the Hubble radius, you can calculate the retarded time is given by this. If you take the final time to be much larger than the initial time, you find the retarded time is just 3 times the initial time. What does this mean in words? The equivalent standard oscillator evolves over just 1 Hubble time, equal to 2i. I go from the initial time ti to 3i. Okay, so what this means is my field system in the super Hubble, far super Hubble domain, if I'm letting it evolve for a very long time, the equivalent standard oscillator is going to evolve only over 1 Hubble time. What does that mean? It means that if the relaxation time for this equivalent oscillator is smaller than the Hubble time, then this thing will not have relaxed yet. It would not have had time to relax, and the equivalent field system will not have had time to relax. Okay? Now, this relaxation time for the oscillator will depend on the state, how many modes there are, and so on. But you see the general idea that there is a suppression, a retardation in the far super Hubble regime. So, and here we go. So now back to these simulations. As I've told you already, this superposition of 25 energy states, we started with an initial non-equilibrium that's a Gaussian. The mode begins outside the Hubble radius. We evolve until it starts to enter the Hubble radius. The way we did the calculation is we performed a numerical simulation for the equivalent oscillator. So on expanding space, what we do is we just evolve the oscillator up to the retarded time. That's why you see these quantities here. This is as a function of retarded time at the time t enter. Anyway, but never mind. This is the time evolution on expanding space. And you see that it's spread out, but not to the full extent of the quantum distribution. With no expanding space, on the contrary, it spreads out completely and matches the Born rule very well. You see the comparison here. Expanding space suppresses the relaxation. Now, quantum noise, the width, the power deficit and all this that we're talking about is just the width of this distribution. So here we are. I give you a mechanism for the suppression of quantum noise at large scales on expanding space. The width here is just as a natural consequence of the dynamics. Smaller, this is the width for the long wavelength, this is the width for the short wavelength. Okay, there's a natural suppression. You can quantify this by, remember the difference between these two distributions, you can quantify it by the h function. Here's a plot of the coarse-grained h function. So this line here is with no spatial expansion. And you see this is log h versus t, getting this approximate exponential decay, very good relaxation. With spatial expansion, it's suppressed. The slope is smaller and it kind of levels off. There is a suppression of quantum noise at large scales. Okay, so what I have here, look, what have we done? We've got a model of, we've got a certain radiation-dominated expansion, a simple scalar field on it. We're showing that you get a suppression of relaxation at large wavelengths. I think that establishes there is a natural mechanism in de Broglie-Bohm theory whereby power can be suppressed at large scales. Okay, that is clear and shown. How now to apply this to cosmology and relate it to what we're seeing on the sky? So the idea, as I said, is that this process, this suppression would take place in some pre-inflationary radiation-dominated era. So that as you come out of that era, you will have a power deficit at large wavelengths. So as inflation begins, there will be a power deficit at large wavelengths. Seeing as there's no relaxation during inflation, this will then feed into the CMB. Now, the latest Planck results tell us that at large wavelengths, that corresponds to this L small, quite small, there is a deficit. There's some, I mean, you see here there's sort of drop, but doing the analysis, there is some deficit whose statistical significance, I mean, when we say the statistical significance, what does this mean? What it means is, if you think about this theoretical ensemble of skies, if you were, if there was no anomaly in the primordial distribution, okay, there would be, what would be the probability of you seeing this? Well, it's, I mean, I'm not sure what this corresponds, is it 1 in 100, 1 in 500? I mean, I'm not sure what this, but there's, you know, there's some small chance, which not very small, it's not 1 in a million, it's not 1 in 5 million, it is, but there's some small but not very small probability that this could just be chance, that the primordial spectrum is actually just normal what you'd expect, and this is just a fluctuation. It could also be that no, actually there is an anomaly in the primordial spectrum, and we're seeing it here. And as the Planck team emphasized, what's important now to better understand and assess the significance of this, you need some physical model that would predict such effects. And the Planck team has emphasized, well, we can't really evaluate this further without having a model that predicts such effects. So here we do have a model. Let me speed up a little bit and say that to get a power deficit in this region, it's straightforward. The transfer functions are known analytically in this low L region. And you can show, if this is the angular power spectrum predicted by quantum theory, and this is the spectrum with non-equilibrium, their ratio will be given by this formula. I've got the square of a Bessel the square of a spherical Bessel function here. Here's my non-equilibrium function, which would be 1 if you're in equilibrium and less than 1 if you've got this deficit. In order to produce a dip in this region, it's straightforward to show that this function, my non-equilibrium function, has to be less than 1 in this sort of region of K-space. Okay, and so roughly, if we're saying that there's some sort of cutoff at large wavelengths in the quantum fluctuations, the cutoff, in order to explain this, has to be, the cutoff has to be of order the Hubble radius today. Okay, so now the question is, could this mechanism produce a cutoff with such a wavelength? Okay, so here we're just thinking orders of magnitude. So here is the kind of schematic picture. Here is a plot. It's not really time. It's the log of the scale factor, which is growing with time. And here's the log of length. So I have physical wavelengths that are proportional to the scale factor. So the log of length just goes as the log of A, with the slope is 1. During pre-inflation, where if it's radiation dominated, the Hubble radius goes as 2t, which is 2a squared. Anyway, the log and the log, the slope here is 2. So you see here that during pre-inflation, you see the Hubble radius grows faster than physical wavelength. Here's a physical wavelength that's outside the Hubble radius, it enters the Hubble radius. At some point, there's going to be a transition from pre-inflation to inflation. Okay, and here I'm modeling it as just some sudden transition. And you can argue that the Hubble radius will increase during this transition, because the way the equation of state has to change in the transition, you can show from the Friedmann equations that there would have to be this jump here. So here now is the point. in this radiation-dominated expansion, here I have two modes. One with, they both have physical wavelength larger than the Hubble radius. During pre-inflation, and they're both, so in this regime here, they're both subject to this suppression of relaxation. This one here enters the Hubble radius before inflation begins. Then you're going to expect it to start relaxing pretty quickly and efficiently. So this mode, by the time it gets through and during inflation exits and feeds into the CMB, it's going to have been in equilibrium. This mode, that did not enter the Hubble radius during pre-inflation, could still be out of equilibrium. And if it doesn't relax during the transition, which is something that has to be studied, it would still be in non-equilibrium during inflation, and then as the wavelengths exit the Hubble radius, generate curvature perturbations that are out of equilibrium. So now there's a simple way of estimating the cutoff. Basically, at early times, the wavelength above which you could have non-equilibrium has to be the physical wavelength has to be larger than the Hubble radius at this time, at the time of the transition. Okay? I can say non-equilibrium is possible for all modes whose physical wavelength at the end of the pre-inflationary period is bigger than the Hubble radius at that time. So my cutoff, physical wavelength is just scale factor times the wave. So my cutoff that I'm after is going to be of this order. Now, there's just some straightforward algebra. The way temperature changes with time in a radiation-dominated expansion, some standard formulas. You have to make an assumption about the temperature or energy scale at the end of the pre-inflationary period. I've assumed that it's comparable to the energy scale during inflation, which seems like a reasonable assumption. The energy scale during inflation, which is basically the Hubble parameter, is of order 10 to the 16 GeV. So in other words, 1,000th of the Planck energy. So taking this to be the temperature at the end of the pre-inflationary period. If you make that assumption, this length scale, this is the length scale today for these modes, comes out to be this. Here's the Hubble radius today. N is the number of E-folds during inflation. During inflation, it's expanding exponentially. The number of, so E to the HT. For a given length of time, you've got HT is some number. It might be 65. And, you've expanded E to the 65. So the number of E-folds. It also depends on the reheating temperature at the end of inflation. It depends on the ratio. What happens, end of the pre-inflationary period, you enter inflation. At the end of inflation, there's a decay of the inflaton field to produce basically a hot Big Bang again, if you like. And the temperature of this is not really known. Estimates range from, this ratio can range from order 1 to much smaller than 1. But in any case, to get a cutoff of order that which is required to explain this, the number of E-folds during inflation, and this ratio has to be of order 10 to the minus 2, which is within the allowed parameter space. According to standard estimates, N has to be of a minimum of order 60, 65, or 70, a minimum. This is going to be, could be of order 1, it could be much less than 1. It's within the allowed parameter space. In order to, make me a bit more sober, let me make one point, that it could be that the number of E-folds during inflation, and in other words, the amount by which space expanded during inflation is so large that, that this wavelength, maybe it's there, maybe my theory is right, this is all correct, but this wavelength could be much bigger than the Hubble radius today, in which case the effect on the CMB would be completely negligible and unobservable. If instead it comes out to be of order this depends on the details of the cosmology and so on. So future work would be to model the transition to inflation and integrate through it, looking at a best fit of this function to data. Something I mentioned briefly, the Planck team have also reported an anisotropy in the same large-scale region. here we have there's no reason why the initial non-equilibrium could also be anisotropic. And we seem to have a single mechanism whereby you could naturally get both a power deficit and an anisotropy, because the initial distribution will relax at short wavelengths and the equilibrium distribution is isotropic. The long wavelength distribution, if it doesn't relax completely, not only would you have a power deficit, it would also be anisotropic. So there's a lot to be studied here. We have definitely a mechanism whereby during this relaxation process you can have a suppression on large scales. How that mechanism will affect what we see depends on the cosmological model. And there are details that still need to be studied, and I'm now collaborating with Patrick Peter on trying to develop this further. And sorry, I'm 5 minutes over time. Not too bad. Thank you. Thank you.